Greetings, fifth period AP chemistry class. This is not exactly how I wanted to do this, but I have come down with something, so this is what we're doing. Um, we're going to go through the last of the notes. Yay, the final part of the notes. It's going to be exciting. Lots of energy in here. Um, it was supposed to be a pun because we're talking about free energy. Talk about creating batteries from chemicals the way it used to be done and still is done today. So let's go ahead and pick up. We start off with a whole bunch of terms and a beautiful diagram of a battery. So we talk about galvanic cells. These are very rudimentary batteries, old school batteries, which most of the concepts kind of carry on into our modern batteries, but we're really not talking about modern batteries. We're talking about galvanic cells, simple chemical battery cells. Let's start off with this picture we have here. We'll zoom in a smidge. So we have two beakers. Notice beaker number one has a copper sulfate solution. Beaker number two has a copper sulfate and zinc sulfate. I think I said the wrong thing already. This is going to be great. A zinc sulfate and a copper sulfate solution. Then there's a piece of zinc sticking down into this solution. There's a piece of copper sticking down into this solution. And this line here is a wire that is connecting them. That allows electrons to flow from one element to the other element. More on that in just a second. And then lastly, there's something called a salt bridge that connects the two. And that salt bridge is going to have a neutral solution in it. And we'll talk about its purpose as well. Okay, so now let's zoom back out. So a galvanic cell is something that turns chemical energy, potential kinetic energy, chemical energy, into electrical energy. Um, and we're going to go back to our old Leo Gur here. We're going to talk about things oxidizing and reducing. Oxidizing and reducing. Let's remember that oxidizing is where we lose electrons, and reducing is where we gain electrons. So there are different pieces to a galvanic cell. First, there's the cathode. At the cathode, we have reduction. This is where electrons are gained. So this side here is labeled as the cathode. I can't quite see it on my picture here, but it's labeled as cathode. And electrons are actually coming down the wire into the copper, and that's where electrons are being gained. Anode, this is where oxidation occurs. This is where electrons are lost. So the zinc loses electrons, and then those electrons travel down the wire to the copper. More on this again and again and again. The salt bridge allows ions to cross over to the other side. And there's something called the electromotive force. This is the actual pull of electrons from one atom to another atom. And then voltage is that electrical chemical potential. So we'll go back into our picture and just kind of explain what's going on here. So we have a zinc solution and a zinc metal, a copper solution and a copper metal. And when they're attached with a wire, a tug of war match occurs over electrons. And those electrons could flow in either direction from copper to zinc or from zinc to copper. What really makes the decision is which one has a stronger electromotive force, similar to which one has a higher electronegativity, which one is better at pulling electrons to it. And in this solution, we have copper ions, Cu2 plus. And then in this solution, we have, I need to get to the insert, we have zincs ions. And so both of those, because they have a positive charge, would be pulling on the electrons. However, based upon some things we're going to get into in a little bit, the copper ions are stronger. And so those electrons get yanked off of this zinc atom right here, yanked off of the zinc, and when zinc loses electrons, those electrons travel up the wire, but the zinc atom becomes zinc ions. Let me say that again. So electrons leave the zinc. I'm going to make a little E with my mouse here. Oh, that's terrible. Yeah. The electrons leave the zinc and they travel along the wire, travel, 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 travel. But when they leave the zinc becomes a positive 2 charge. So it's actually losing 2 electrons. I'm not going to try to put a 2 out there, but the zinc is becoming zinc plus 2. And that electron travels along the wire, travels along the wire. Oh, hi, I'm copper. I don't need any electrons. I already have some. And then when it comes into here, it's going to go into the solution. What would happen if those copper ions gained electrons? If those copper ions gained electrons, they would become copper metal. And so some of those copper ions start to stick to this copper metal. So let's start this all over again. We have a solution in one beaker on the left. We have another solution in the other beaker on the right. The first beaker is zinc and zinc sulfate with zinc ions dissolved into the solution. The other beaker is copper metal and copper sulfate with copper ions dissolved in the solution. The copper ions are stronger at pulling electrons than the zinc ions, and so they pull the electrons through the wire, and as the electrons hit those ions, those copper ions go back into being copper atoms. So this piece of copper slowly gets bigger and 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 bigger. As electrons come through the wire, ions turn back into atoms, and the size of this wire slowly grows. The size of this copper metal in the solution slowly grows as some of those ions become solid. That's probably enough. On the other side, let's go with a different color. We're going to go with we'll go with white. On the other side, zinc atoms are disappearing and becoming zinc ions. I'm leaving little holes, which is a little bit of a misnomer, but I'm just trying to show that some of them are missing. Zinc atoms are leaving the metal and becoming zinc ions. Okay, that's pretty good. I like this drawing here. So the zinc atoms are becoming zinc ions. The copper ions are becoming copper atoms. And as the electrons flow through over here, we'd slowly get a buildup of negative charge on one side. And this is the side where we would have a negative charge because electrons are coming through. And then on the other side, we would have a buildup of a positive charge, wouldn't we? Well, it wouldn't take long for those two buildup of charges to cause the electrons to get pulled right back. And this is where the salt bridge comes into play. The salt bridge allows that charge to be continuously flowing. And so the negative ions here, the negative that builds up in here, and the positive that builds up in here is going to draw ions out of the salt bridge. The positive ions, the potassium, are going to get pulled towards the negative, and the chlorine, the negative ions, are going to get pulled towards the positive. And so we end up with, overall, a loop. We end up with a negative going, negative going, negative going, negative going, negative going around this way. And then it gets in the solution. And then the negative can go down the tube too. We have a complete circle, or as they say in electricity, we have a circuit. We have a complete loop where the charge can move in a circle. Now, half of that charge is electrons flowing through the wire, and the other half of that charge is ions moving through the salt bridge. So, this is the basics of galvanic cells, is that Electrons get pulled from one metal or one atom to the ions of another through a wire. Now, if we cut this wire, let's just talk about simple scenarios here. We chop this wire, electrons can't flow because it's cut. When we open the wire up, we disconnect it, electrons can't flow. And that's, the same thing as you flick your light switch off, and now the electrons can't flow, and so your light bulbs all go out. Flick the light switch on, you connect the wire, and the electrons can flow and power something. Okay. Um, so now we need to know how we know which direction the electrons are flowing. So, so in this two reactions we have here, we are going to look and try to figure out who is losing electrons and who is gaining electrons. So I've already got it worked out, but let's just try to remember this. This magnesium here is becoming magnesium plus 2. Magnesium is becoming magnesium plus 2, which means, excuse me, it is losing 2 electrons. So if it's losing electrons, this is where oxidation is. Remember, Leo? And then the hydrogen is going from plus 1. And on the other side, that's normal hydrogen, which does not have a charge. If you go from plus 1 to 0, no charge, you're gaining electrons. So here we have a new phrase that we're going to use a great deal. A Leo cat gers. A stands for anode. Leo is the same thing we already know, lose electrons oxidation. That's anode, lose electrons oxidation. Cathode, gain electrons reduction. So that is anode and cathode. I'll type those in right underneath the words. Anode and cathode. If you've ever looked at a battery, which I'm sure you have, the anode is the negative and the cathode is the positive. And then in the manganese one, the manganese, take a second. Feel free to pause the video for a second and see if you can figure out what manganese's charge is here in the permanganate. We used to do that all the time. I'll zoom in there. I don't know that if I can write on this screen very well, but we used to do that all the time. We'd come in here and we'd say, oxygen's a -2, and the four oxygens together are a -8. When we add the manganese, which I'll put as X, and the oxygens together, see this charge here? It equals -1. X plus -8 equals -1. What is the value of X? And then we would say manganese is a +7. Here we go. Evidently, I can write on the screen with my finger. That's very nice. So the manganese is going from +7, gaining 5 electrons, and now it's +2. It's the cathode. It's where it's gaining electrons. Catger. The iron is going from +2 to +3. It's losing 1 electron. But there are 5 irons, so that's happening 5 times. 5 times 1 is 5 electrons being lost. Yay. So the iron is at the anode. Back to my thing from a minute ago. Oop, drawing on the screen. That's not going to work. The anode is where we lose electrons. Look, the zinc was losing electrons. They were traveling through the wire. The cathode was gaining electrons. The electrons were traveling through the wire, and the copper was gobbling them up. So in these, all right. Um, so in these two reactions, we're saying that the magnesium is the anode, or the electrons would be going up the wire out of the magnesium, and then those magnesium atoms are becoming magnesium ions, and the solution is getting more and more magnesium ions. And as those electrons travel through the wire, they go to the other side, and then the hydrogen atoms gain the electrons, and we make hydrogen H2. Hydrogen H2 is a gas, so on the other side of the battery, we would see bubbles of hydrogen gas being formed, which would be kind of neat. In our second reaction, the permanganate side is the gaining the electrons, and so be going from permanganate to manganese. And then the iron would be losing electrons. And these are both ions. So somehow the electrons are being removed. Interesting. In this one, I'm going to guess. So we don't actually have solid iron in part B. So a lot of times when we don't have solid iron, we just have like a solution and a solution. We need to have something to deliver the electrons. We need a substitute cathode or something like that. We need an inert metal to deliver electrons. A very common inert metal is platinum. Yeah, platinum's a great metal. It's not very good at giving up its electrons. Gold is also very good, but platinum's a little bit better than gold. And so what they would do is where the copper was stuck into the solution, they would just have a piece of platinum stuck into there. And the platinum would be pulling the electrons off of the iron, turning it into iron plus three. And then those electrons would go through the wire. Yeah. So there'd be a piece of platinum stuck in the solution. All right. So we've reviewed the Leo and the Ger, how we can identify them in the reaction. Now we get to talk about voltages and cell potentials. So both of these are written as magnesium is losing two electrons and copper is losing two electrons. And the issue with that is that not everything can be losing electrons. Something has to be gaining electrons. Something has to be gaining electrons. Excuse me. Something has to be gaining electrons. So if you made two halves of a battery, one with magnesium and magnesium ions, one with copper and copper ions, and you connected them all together, salt bridge wire, one of these reactions has to flip around and go the other direction. So what do you suppose would happen if one of these reactions was written backwards to the voltage? Use your Hess's law brain. What would happen in Hess's law if you wrote a reaction backwards? Well, the exact same thing here happens to the voltage. The voltage would change from negative to positive or positive to negative. You write it backwards. Um, However, this is a big one, like big, 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 big. So let's actually write some clear notes here. Flipping a reaction reverses the plus slash minus charge of voltage. That one probably makes perfect sense. Flipping a reaction versus positive to negative or negative to positive for the voltage. All right. However, and this is a big however, I'm going to write like all caps. I'm screaming at you. However, multiplying and dividing have no, yes, I said no impact on voltage. What do you mean by that? I mean, if we did two copper makes two copper positive two plus four electrons, that still has a voltage of negative 0.34 volts. Doubling the reaction has no impact on the voltage. Doubling the reaction has no impact on the voltage. That feels like I'm saying something wrong because that's very different than Hess's law. Okay? Um, but flipping a reaction does change the voltage. What does doubling it change? It changes the number of electrons, which changes the electrons per second. That's called amperage. We're going to deal with amperage a little bit later in the notes. Voltage is how much potential a reaction has. Amperage is how many electrons a reaction has. We're not dealing with amperage at all right now. So multiplying a reaction and dividing a reaction have no impact on the voltage. All right, that felt a little weird. Um, Sorry I sounded cross, but I kind of had to. I needed to make a big impact. I'm going to switch this to red because, man, red is scary. And we need to make sure we got that. Okay, flipping a reaction reverses the charge from positive to negative. However, multiplying and dividing has no impact on the voltage. Great. Um, so I have flipped the copper reaction around in my next part of the notes. By flipping the copper reaction around, when I add these together, then the voltage is 2.37 from the first beaker, 0.34 from the second beaker for a combined voltage of 2.71. Magnesium is losing electrons, so it's the anode. Copper is gaining electrons, so it's the cathode. All right, and we're gonna kind of keep our eye on some issues. The one being that the oxidation and reduction half reactions must have a greater than zero voltage. That's a fancy way of saying that we want we want the text box tool. We want to have positive voltages in galvanic cells. So we are looking for positive voltages when we combine them together. Okay, make that big. We're looking for positive voltages in galvanic cells. Anytime we combine two reactions together, we want to check and see that the combined voltage is negative. We want to make sure that somebody is losing electrons and somebody is gaining electrons. So question 2, using the data above, calculate the EMF, also known as the cell potential, for each, the electromotive force, for each of the reactions. Is it a galvanic cell? If yes, ID the anode and the cathode. So magnesium becoming magnesium plus 2. Just a second ago, right here, it said magnesium becoming magnesium plus 2 is a 2.37 volts. And then hydrogen becoming H2. Here's H2 becoming 2H. Let's flip this reaction around. 0 volts becomes negative 0 volts, still 0. So hydrogen, this reaction here, A, the combined voltage of that reaction, we take the anode and the cathode voltage and add them together, and we get 2.37 volts. That would be a galvanic cell as written. So magnesium is where the anode's at, it's losing electrons. Hydrogen is where we'd find the cathode, it's gaining electrons. Whereas the second reaction, copper becoming copper plus 2, copper becoming copper plus 2 is negative 0.34. Uh-oh. Copper plus 2 becoming copper is positive 0.34. Okay, I have it right. That's positive 0.34. And then silver becoming silver plus 1 is up here. It's negative zero point 0.8. I add those together, that's negative 0.46 volts. With a negative voltage, this galvanic cell would not work as constructed. So you've built this battery, you've stuck copper in and silver in, and you've like got a light bulb set up there. So as the electrons flow by, maybe the light bulb lights up, and you're hoping the electrons are going to flow one way through it, but actually the electrons are going to flow the other way because you have it built backwards. So when you have a negative voltage, it's not really flowing the way you want it to. It might not be flowing at all because um, a lot of equipment, like light bulbs, only allow the electrons to flow in one direction through them. There's some things going on in there I don't really quite understand that only allow the electrons to flow one direction. And so, since you've constructed your battery backwards, they're not going to flow. Couldn't we just turn the whole thing around? Yeah, sure. That's a great idea, Melissa. I like this idea. Let's just flip the entire thing around. We put the products on the reactants and the reactants on the products, which really just means when we put the light bulb in up here, we're turning the light bulb around and then everything's going to flow. That would work just fine. Yeah. Okay. Moving on. Um, all right. Number three, given the half cells, decide which is the anode and the cathode, write a balanced overall reaction. Oh, I forgot to do that. Dang it. I forgot to do that. Um, okay. Well, we need a positive voltage. Um, and we need one of them to be the anode and one of them to be a cathode. Right now, they're both gaining electrons. So one of these reactions has to be flipped around. They can't both gain electrons. Somebody has to lose the electrons for someone else to gain them. So we are going to, what we're going to do here is we're going to figure out which one we can flip and still have a positive voltage. If we flip the second one, we'd have a negative and a negative added together. That's not going to work. If we flip the first one, that would work. We'd have positive 0.23 and 1.3 with a total voltage of 1.46. However, I forgot to write the flipped version of this, didn't I? Did I? Yes, I did. I did. I forgot to write the flipped version of this. Let me write that. So it would be oh, the electrons aren't equal either. I can't gain 4 electrons if I'm losing 2 electrons. So I need to double that first reaction. So two, what the heck? Just a second. That was emergency. Two nickels atoms making two nickel ions plus 4 electrons. And that is going to flip our voltage around to positive 0.23 volts. Remember, flipping a reaction changes the voltage from positive to negative. Doubling the reaction has no impact on the voltage. So I changed the voltage because I flipped it, but I did not change the voltage by doubling it. Um, you know what? I should have done the same thing in this second one. Which one am I supposed to reverse this time? Not the first one. If I reverse the first one, I'll have two negative reactions. I need to reverse the second one. Are my electrons equal? Oh, they're not. Dang it. Put two here, two here, and two here. I've just doubled my reaction. Then I'm going to flip this reaction around. Sn becomes Sn2 plus and 2 electrons. And that's going to flip this voltage to positive 0.14 volts. There we go. Okay. And then over here on the right, I kind of wrote some of that stuff out. We need a positive voltage. We flip the first reaction around. Now it's oxidation because it's losing electrons. And now I've got it written at least. And the second one is gaining electrons. It's reduction. Here's the total voltage for these two cells combined together. I keep saying cells. We refer to each beaker as a cell. And so the combined batteries, combined cells. All right. We'll be back to this slide in just a second. We're going to introduce a little bit of notation items, something called line notation. Line notation is just a way of illustrating real quickly who the main player. All right. So we have gone through the four parts of a galvanic cell. We now understand how to look at cell potentials or voltages and flip them around to figure out, which direction the electrons would flow so that the cell potential is positive. Yes, the voltage needs to be positive when we add them together. The anode is where we're losing electrons. The cathode is where we're gaining electrons. We have to have one of each. We must have someone losing and someone else gaining electrons. And then this last thing, line notation, which is not nearly as exciting as some of the other stuff, just showing how the electrons are moving around. Okay, now let's try it all together. So take a second, look at number 4, pause the video, and try to go through all of those steps. Try to calculate the cell's voltage, which reaction should be flipped around. After you flip them around, how do you add it together? What's the total? Does any reaction need to be multiplied? Does that have an impact on the voltage? And then make the line diagram like we did a little bit with the anode separated by two lines that represent the salt bridge and the cathode. All right, go ahead and pause and try it. If you didn't pause, then you probably just noticed that I just kind of stared at the screen for a second. I think I almost fell asleep actually. Um, but as I'm looking at this, I see that they're both positive values. So when I flip one of them around, because they can't both be currently as they're written, they're both gaining electrons. One of them has to lose electrons. It can't be the second one. If I flip the second one, I'd end up with a negative voltage. So I flipped the first one around. I did that. Flipped the first one around. And then I realized, gosh, I need to have 6 electrons. So I'm going to triple that. However, when you triple it, it doesn't have any impact on the voltage. It's still 0.34. It's just negative because we flipped it. Then the total voltage is the two values added together. A negative 0.34 and 1.33 is 1.9, is 0.99. And then I wrote line notation. Copper's becoming copper ions. It's losing electrons. I feel like there's something else hiding there. Oh, right. The anode is the copper becoming copper ions. The cathode is the dichromate becoming chromium ions. Lots of electrons exchanging hand. It looks pretty good. Yeah, pretty good. 6 electrons. Cool. Okay, that's the basics of galvanic cells. We've hit all of that. Now we're going to kind of wrap back into Gibbs free energy as it's related to galvanic cells. We have another equation that's on your equation sheet. Don't need to have it memorized by no means. Um, well, let's rediscuss with G, delta G, the Gibbs free energy value. You want to have a negative value for a reaction to be spontaneous. For delta G, why did that not make a text box? Let's try that again. You want a negative value equals spontaneous reaction. Ooh, that looks really gross. Oh, whatever. Okay. For delta G, a negative value equals a spontaneous reaction. Okay? So that was from the first half of the notes. We had delta G. Now we're seeing delta G is equal to negative N, which always means moles. In this case, it means the moles of electrons. F, which is a constant. Look at your equation sheet, and you will see this constant is written there. I don't think it's this value. I think it's 96,500. But if it's this value, it's this value. And then E. So I feel like this says 96 comma 500 on the equation sheet. But so I'm going to proceed as if it's 96,500. I might be wrong. I don't have an equation sheet here at my house. Um, so we plug values in. Oh, E is the voltage. E is the voltage. Voltage is in joules per coulomb. Faraday is a constant in coulombs per mole. Then we're multiplying by moles. We're basically multiplying moles of electrons times coulombs per mole, moles of electrons times coulombs per mole. Moles would cancel out. You have coulombs. And then we're multiplying it by joules per coulomb. So coulombs would cancel. We just have joules. Coulomb is a unit of charge. We're not going to get too much into what a unit of charge is. But let's go ahead and do a math problem because that's what we're really about. We're doing the math. So the next page, we have number 7 in the notes. We have a voltage of 1.1 volts. Let's calculate delta G for this reaction. And the question just says, will zinc think it's supposed to say, will zinc react with copper spontaneously or something like that? And so one of the hardest things kids struggle with is figuring out the value of N. For this reaction, N is equal to 2. Well, why? Yeah, N is the number of electrons that are being exchanged. So if you dive into that reaction, zinc is becoming zinc plus 2, so it's losing 2 electrons. And copper plus 2 is becoming copper, it's gaining 2 electrons. So there's 2 electrons exchanging. So N is 2, the number of electrons. Then we just plug in the other values, the Faraday's constant, 96,500, and the voltage that was given right up here, 1.1 volts. We multiply them together. Don't forget there's a negative sign at the front of this, negative NFE, and negative 2 times all that stuff is negative 212,000, or negative 212, negative 212 kilojoules. Anyway, it's a negative value. And when delta G is negative, reactions can occur spontaneously. And the conditions are all set for this reaction to run. We connect it up and it will run. The electrons will flow. They'll move around, which is great. Okay? Really, it's awesome. That's how batteries work and stuff. Um, as the reaction flows, come back to our very first picture. In this very first picture, what I never mentioned to you was the molarity of things. I never mentioned that because there were just too many things going on. I really didn't want to distract you by adding another thing. This is supposed to be a 1 molar zinc sulfate solution, and the other one would be a 1 molar copper sulfate solution. But yeah, I just had you flip all the way back to the very beginning of the notes again. Both of those would be 1 molar. Now, as the reaction goes, though, remember this little cute drawing I did where I was like, look, I can make orange dots and I can make white dots. The orange dots meant that copper ions were becoming copper solid. What is happening to the molarity as this reaction rolls? Well, it's eventually going to become 0.99 molar on this side as the copper ions become solid, aren't they? It's going to slowly drop. What's going to happen on the other side? It's going to become 1.01 molar as the zinc ions appear. As those zinc ions appear. Why are you moving the wrong thing? There we go. So the molarity of these solutions is going to start at 1 and 1, but the second you connect the wire and those electrons flow, the reaction is occurring, and you have a buildup of zinc ions, so that molarity slowly increases, and a drop of copper ions, so that molarity slowly decreases. Now notice we have the reactions written at the bottom here. We have gaining 2 electrons and becomes zinc ions. The zinc ions are a product. The value of our products is increasing. The copper ions are a reactant. The value of our copper ions, the reactant, is decreasing. That's going to change the scenario. As the reaction flows and things start to move around, we are going to see changes in the voltage. And so there's an equation for that. This is called the Nernst equation, and I am positive that I just butchered the pronunciation of that man's name. I looked it up. I'm still not sure how to say it. There it is right there. Let's try clicking on that again. Greens works. The Nernst equation is for calculating voltage when you're no longer at 1 molar. Okay? If you were at 1 molar, first let's look at this equation. The voltage of the cell is equal to the normal voltage of the cell. Notice a little prime or degree sign, the perfect voltage as we've been calculating it the entire time. Let's see if I can find that later. Um, or the perfect voltage of the cell. So the voltage of the cell is equal to the perfect voltage of the cell minus this combination of RT over NF, where R is the value of R that's got joules in it. T is the temperature. This one's at 25 degrees Celsius. That'd be 298. N is the moles of electrons, just like we did a second ago. F is Faraday's constant, 96,500. Just plug in all of those things. And then the natural log of Q, the reaction quotient. Now, remember, reaction quotient, just like K, is the products over the reactants. Products over the reactants. What would happen if the products over the reactants were both 1? We'd have 1 divided by 1. Q would equal 1. Then we'd have the natural log of 1. Landon, what's the natural log of 1? Did everybody hear him? He said 0. Good job, Landon. It is 0. Good job. I know you would know that one. What is 0 times RT over NF? 0. So the voltage of the cell is equal to the standard voltage of the cell if we have 1 and 1. But as the reaction runs, we're going to have a buildup of products and a decrease of reactants, and this voltage is going to slowly drop. Very, very slowly drop, like decimal places. Went ahead and did a problem here on the next page. Um, Calculate the E for this galvanic cell based off the half reactions. First thing I noticed when I looked at these two reactions is that both of them were gaining electrons, and that's a no-no. They can't both gain electrons. So then I realized I needed to flip the top reaction around so that when I added the two reactions together, the voltages would be a positive voltage. And so that is the standard cell potential or standard cell voltage, E prime. While I was explaining this reaction, so let's just try this again. I was in the middle of explaining this equation here. So I'm just going to kind of hit the pieces again. Um, we have the standard voltage, we have standard voltage, we have R, which is 8.31. We have the temperature, that's not a problem. There were two electrons, so N was 2. Faraday's constant is 96,500. And then the pieces people struggle with, cadmium is on the product side. Notice it's to the right of the arrow. So this value is a product. It needs to be on top. It's products divided by reactants. Lead is on the left side. Lead ions are on the left side. So lead ions are reactants. Reactants go on the bottom. Okay? You might be saying to yourself, well, what about the other things in that reaction? Um, Cadmium is a reactant, but it's a solid. So it's in there as a 1. Lead is a product, but it's a solid, so it's in there as a 1. So these are both in here as 1s. Um, but the real point is changing those voltages and having a lot more. This is 10 times the amount of reactant to product has barely changed the voltage. We changed it by about uh, 10%, I think. A tenfold increase difference in molarity caused a 10% increase. That means you can't really get a huge change in voltage. And as the reaction runs, you're going to lose lead, so your voltage is going to slowly drop. You're going to gain cadmium, so your voltage is going to slowly drop. Okay. All right. Now we're moving on to electrolysis, which is the opposite of voltage. Electrolysis, I mean, it's the opposite of a galvanic cell. With electrolysis, we are forcing everything to go backwards. This is recharging the battery. Okay. Um, Recharging is not actually conceptually difficult. We would just need a stronger battery to recharge it, conceptually speaking. In actual recharging your battery, there's a lot of things that happen. But let's just break it down to the smallest concepts possible. This reaction won't run because it has a negative voltage. What if we put it in with our battery from earlier, which had a positive voltage, right? This one is 1.1 volts. And so if I put 1.1 volts and connect it with a wire. Like I go from zinc to the copper to the iodine, back and around, and make a loop, make a circle, 1.1 and negative 0.19, this reaction can be forced to happen because of that extra voltage we're applying. And that's what electrolysis is. It is forcing a current, it's forcing a current through a cell that doesn't want to do that. It's making a chemical reaction occur that doesn't want to do that by using a stronger reaction to make it happen. Yeah, okay. That's what electrolysis is. All right, so reaction rates in electrochemistry. How long is a reaction going to last? Depends on how many electrons you're letting flow through the wire in a second. Um, so here we have an equation, I equals Q over T. I is the amps, Q is the charge and coulombs, and then T is the time. Um, so the units for current are amperes, but that's really coulomb divided by seconds, coulombs per second. And then we often will combine this with Faraday's constant. And so if we think about, I'm going to write C for coulombs, coulombs per mole of electron, and then we multiply that or divide that by the amps, the amperage. Um, we can combine these things together because of their units. We combine them together and do some fun math with them. Of course, we know that a mole of electrons is equal to Avogadro's number also. Let's look at an example of this weird thing I'm talking about. Let's go to the next page. Um, a battery is connected using copper and magnesium. It runs for 45 minutes. The mass of the magnesium is measured at 4.24 grams before connecting the battery. Afterwards, the magnesium is measured at 4.16. Well, that's because the magnesium's becoming magnesium ions, so we're losing some mass. All right. Draw the battery, label the anode, cathode, salt bridge, direction. I'd like you all to do that. The magnesium is losing electrons, so it should be the anode. The copper is gaining electrons, therefore the copper should be the cathode. After you draw those two beakers, you got the magnesium in the magnesium solution, you got the copper in the copper solution. You need to connect the two pieces of metal with a wire. And then each beaker needs to have some sort of salt bridge. The salt bridge would have some sort of, probably like sodium chloride, that's a good salt for the salt bridge, or potassium chloride, some simple salt in it to allow the charge to move around. So the magnesium goes from 4.29 to 4.14. We lose 0.13 grams of magnesium. We can do a little bit of fun stuff with that. We can say, well, 0.13 grams of magnesium. We know that 1 mole of magnesium is 24.32 grams from the periodic table. We're converting mass to moles. In this reaction, for every magnesium, there's 2 electrons. Yeah, there's 2 electrons. Um, and then that is for every 1 mole of electrons, there's 96,485. That's Faraday's constant. We now know how many coulombs of charge have just moved through the wire, 1,031. It took 45 minutes. So I'm going to say the charge, I'm down here. Let me kind of highlight where I am, what I'm doing right now. I'm using the equation I equals QT, or okay. Where was I? Yeah, my camera cut off for a second, and I just realized that as I was all done. I thought I was done. So I equals QT, where Q is that charge. It's the number of coulombs, 1,031 coulombs. T is the time. I converted 45 minutes into seconds. Uh,
because amps is coulombs per second. I know it says Q divided by T, but T is supposed to be in seconds. So coulombs per second, we have 0.382 amps. I think the thing I kind of also typically want to hit on here is that earlier we were talking about when you flip these reactions around, you're changing like the cell voltage from positive to negative. And now maybe what if we're doubling them? So I'm actually going to try to draw something and kind of illustrate what's going on here. This is going to be pretty ugly, so bear with me. So when we talk about cell potential or voltage, we're talking about how far something can drop. So we have this potential, we have an object and it can drop. And every time copper, I would say magnesium, every time magnesium gives away 2 electrons, those electrons have a potential of dropping 2.73, 2.37. That potential is not going to change because every time magnesium is becoming magnesium plus 2. Every time magnesium is becoming magnesium plus 2. So that's the exact same drop, consistently, consistently, consistently. So all we're measuring is how much energy is given off as magnesium gives off 2 electrons. Now you might notice though that I have 1, 2, 3 sets of 2. So I'm not changing the voltage though. I'm not changing their potential to drop. They're all still dropping the same amount, changing how many are dropping. And when we talk about how many, we're talking about reaction rates. That's what we're talking about the amperage. Amperage is how much per second, right? The amperage is how much per second. Now the copper was 0.34. So you have this 0.34, 0.34, 0.34, 0.34, 0.34. So it's like the electrons are dropping and then they're dropping more. So we have this combined voltage. And then lastly, earlier, let me get rid of all of these. These are the last that would be better. Whoa, I love the last. Delete. Earlier, we had something like a negative voltage. Where was that? Oh, it was in the electrolysis. It's right here. It's something going through electrolysis, negative 0.19. So let's imagine that we have this battery, the magnesium and copper, that's 2.71 volts. And you have just a second. You have the magnesium beaker, and you have the copper beaker. And so a piece of metal, wire, salt bridge, right? And then there's a solution. And that's your entire magnesium and copper beaker. That's the entire cell. Well, if you want to force that other reaction to occur, here's how you would do it. Okay? So what we would do is we would insert that other reaction in between our 2 beakers that are actually functional. So we have one reaction, whoop, second beaker, and then back to orange. There we go. And this is pretty ugly. Give me a second. Not working on all cylinders here. I just want this. Oh, gosh. Um, 1 second. I figure out how to erase this. There we go. Okay. This would still be connected to this piece of metal. Okay. Sorry, guys. I've been fighting that all night. The salt bridge would then go to here, wire, salt bridge, and I didn't draw it very well, but the beaker that doesn't want to react would be put in the middle of the 2 that do react. So these two beakers that are 2.7 and this reaction that is 0.19, you would put them in line. So it'd be like from one to the other to the other. And I haven't done a good job drawing it here. I'm sorry, guys. But this is what you would do. You would line them up so that the one reaction would pull the other reaction along and force it to occur. Um, and we often do this with our electric sockets and things. The voltage in an electric socket is usually around 110 volts. Also a lot of amps. It's somewhere between 15 and 30 amps, which is an insane amount of amps. And then you plug in your little adapter, a little square brick thing. You plug that into the wall, and then adjust the voltage and the amperage to something that your phone can handle, so that you don't burn your phone out. If you use the wrong block, you use somebody else's block, or maybe you use your Chromebook charger. That's going to have a different amperage and a different wattage and different voltage and all those things. And it could very well burn out your battery if you're not careful. All right. Speaking of burnt out, I think that I am burnt out and I am going to stop this video. Go and try the homework. You have plenty of time left in class. Start digging through the homework. Good night, guys. I'll see you when I can. Bye.